Well, welcome to physics class, and we're starting chapter 27. Chapters 27 and 28, which are the last two chapters we're going to do this year, take us into modern physics as it's defined. We've been doing a lot of classical physics, then we did electromagnetism and a few other things that do take us into other areas, most of which is still considered classical physics. We did classical mechanics before, and then we do classical physics, and this is modern physics. And this is something that you should have some exposure to before you leave high school. We're not going to go as deep into it as we could. When I was in college, we took a whole class on modern physics, and I took a graduate school on quantum physics, graduate class on quantum physics. But just an introduction to this. We're going to start with what is called Galilean relativity. This refers to Galileo Galilei. And so this is relativity that goes back to the times of Galileo. So this has been around for a while. They started talking about phenomenological relativity. Phenomenon means things you observe. And they started with the man on the treadmill. And they tell the little story in your book about a man running on the treadmill for all he's worth. And he's going to make his 5-minute mile or whatever it is. And his wife calmly walks up beside him and invites him to supper. He's moving, but only relatively. In fact, not even really. Relatively, he's moving. But anyway, relative motion, only relative motion has meaning. And why they say this and they repeat it is that there is no absolute reference point by which all motion is judged. This is not related to moral relativity. We're going to talk about relativity in physics. Simply, it means that there's no simple spot from which you can observe the universe and it be the one spot by which everything else is judged. When it comes to ethics and morality, we do have such a thing. God himself is, in fact, an absolute point by which we judge everything else. We don't have that in motion. So relative motion is all we have. And relativity is emphasized in the study of objects in one reference frame as seen from another reference frame that is moving with respect to the first. So buses, trains, boats, cars, all of these are good examples. Even a football field, when you have one person, the quarterback standing still and somebody running and he wants to throw the ball to them. That's a moving reference frame. Okay. So you have because each person's reference frame is from their own perspective, or we can look at it from each person's own perspective. And Galileo Galilei applied this relativity to mechanics. Okay. So this is a classical mechanical relativity. They want us to get Galilean relativity understood before we try to do Einsteinian relativistic physics, okay? So Galileo stated that the laws of mechanics are the same in steadily moving reference frames as they are in resting reference frames. And this is called Galilean relativity. Okay, so what he's saying is if an object is not accelerating, steadily moving, then the laws of mechanics are the same. So all that stuff we learned, F equals ma, Newton's three laws, which F equals ma is one of those, the laws of motion, the three equations of motion, all of that stuff is going to be the same whether you are steadily moving or if you are resting, because technically even resting reference frames are moving relative to something else. Okay, so his simple experiment was a boat. If a boat were standing still and you dropped a ball, you would expect the ball to drop straight down. If the boat is moving, it still drops straight down as far as the boat is concerned. Okay? And the logic behind this, if you stop and think about it, actually does work out. Because the ball is moving forward with the boat. When you drop it, it's still moving forward with the boat, but now it's also falling. There's no force on it to move it from the direction of the boat. Now they're assuming no major wind or something like that. But even if there was wind, then you'd have another force, which would cause an acceleration of the ball. But it wouldn't be because the boat's moving. It would be because the wind is moving, the air is moving. Another example that they give, and as I pulled these out of the book, there's a man on the boat walking. You can't see him really well in the picture, but you can see him in the binoculars. And so the boat is moving, and so is the crewman. And so the guy on shore, when he looks at the crewman, he sees the crewman moving the boat speed plus the person's speed. So he's moving faster. If you were on the boat, you would see the man moving just at the man's speed. But when you're standing on shore, you see the boat and the man both moving, and they would add together. If the man were walking the opposite direction of the boat, you could actually see the man standing still. Like you'd look out and the man would just stay right in front of you, and the boat would pass underneath him because he's walking backwards. relative to the boat, opposite the boat. Okay, so this is kind of a quick idea of how this all is going to work. Okay, so let's do Galilean coordinate transformations. Galilean here is what the G stands for. Now, in your textbook, they give a pictorial example for you, and they give a little story about this. There's a teacher, at the end of the year is taking a vacation on the beach. He relaxes in his floating lounge chair offshore, reading Newton's Principia, and the current is taking him out to sea. And eventually they're coming to find him, and there's a guy on shore watching, looking out and seeing the teacher out in the ocean, and then there's a helicopter flying overhead, which is also observing this teacher in his boat, or in his chair. And they're going to use two different reference frames. Okay, the officer on shore is using X, Y, Z, and T. The helicopter pilot is using X prime, Y prime, Z prime, and T prime. So here's a picture of this. There's the officer on shore, and he's looking at things X, Y, and Z. And the helicopter is also doing X, Y, and Z and I'm sorry, I might lose my train of thought here a little bit. And they're both looking at the teacher. And what we want to do then is to compare their two reference frames, their X, Y, Z, and T reference frames. One of them is just the regular, the other one is prime. And so we want to see how would you convert from one reference frame to the other reference frame. So the officer has to translate the helicopter coordinates. So the helicopter says the teacher is at such and such a location. Well, then he needs to be able to translate that to his own reference frame so he can figure out where to look. So from his perspective, he's going to need to take the helicopters in the X direction. The helicopter is moving in the X direction. Because the helicopter is moving in the X direction, his coordinate system is moving, okay? And it's moving away from the officer. So the officer's looking at something and saying, okay, in the X direction, I have to take where the helicopter says it is and add to that how far the helicopter has come in the X direction. And I want to clarify something here quickly. He's flying away from the beach. Okay, he's flying away from him. Yeah, that's what, as I said. Now, in the Y direction, this is the way they have this set up. This is the left-right direction. The helicopter's flying straight out the X-axis. So the Y is exactly the same. Now, the helicopter is 50 meters up in the air. And so everything he's seen from 50 meters up in the air. For the officer, he has to add 50 meters to everything he says, because otherwise he's going to get the wrong answer. For example, the teacher in this chair is on the ocean. Well, because the helicopter is 50 meters above the ocean, the teacher's position in Z is going to be negative 50. But to the officer, it's going to be 0 because he's on the ocean, which the officer is also at the ocean. And so he's going to have to add, the helicopter says negative 50, you add 52, you get 0, so you get the right answer. And then T equals T prime. Time is the same in both coordinate systems. Now, looking at the first one, going back to the first one, because that's the most difficult one, the key is a helicopter starts at the shore and is flying out. And so wherever he says something is at X, it's going to be behind him. And you're going to have to add to that how far he's traveled to figure out how far he is from the officer. Okay? I'll try to keep making this make sense. This is probably the most challenging part of it. So the pilot must translate the officer's coordinates. And so they're going to be the exact opposite. They're just basically once you have the one, the other one's just a matter of algebraic solution. Okay. If the officer tells him where the teacher is, the pilot has to calculate in the X direction how far he has traveled from shore and subtract that from what the officer on shore is saying. Okay, so let's talk about inertial reference frames. An inertial reference frame is defined because the laws of mechanics have the same mathematical form in every reference frame that does not accelerate, and that is defined as inertial. So an inertial reference frame is a reference frame that's not accelerating. So it's moving at constant speed. It can be moving at any speed in any direction, but it has to be a constant speed, no acceleration. When you get acceleration, you can still do some of the laws of mechanics, but you have to throw in a factor for the acceleration and accommodate for acceleration. We actually did that when we talked about weight and falling objects. We did that, worked with accelerating reference frames. So back to the beginning of the chapter, only relative motion has meaning in mechanics. So what are some problems arising from Galilean relativity? Why did we learn it? But what's wrong with it? Well, it doesn't work for light. Okay, that's the key thing. It doesn't work for light. Which means in the next section, we are going to talk about what happens when you do deal with light. They went into a lot more detail with that, but I'm not. No, I'm not. Okay, on your review page, pull your review page out. We need to do some things on your review page. I'm helping you do your homework in this section. These couple of chapters, we'll do your homework together like we kind of did in the last couple of chapters as well. So number 1.1, terms. Okay, first term is inertial reference frame. And an inertial reference frame is a non-accelerating reference frame in which the laws of physics apply. Okay, that's what the whole point of inertial reference frame is. Just talked about it. It's not accelerating, and because it's not accelerating, the laws of physics do apply. All right, we're going to look at this diagram here on the left, and we're going to do some coordinate conversion type activities. Okay, so according to the hiker, what are the coordinates of the clock? So if you look at the hiker, and if I did my calculations right, that clock is sitting at 5:2. Okay, if you go over 5 and up 2, you find the coordinates of the clock, 5:2. Now, if you're looking at it from this point of the chair, what are the coordinates of the clock? Well, from the chair, you go over 3, down 2, so it's 3, -2. So the point is, from the two different reference frames, the clock is at two different places. So how would we transform from the one to the other? Well, in the x direction, now we're going from the hiker to the chair. So the chair is our final result, so that goes on the left side of the equation. The hiker is where we're starting with. So if we take the hiker's coordinate, now we're looking at the clock particularly. The hiker says it's at 5. The chair says it's at 2, so it's going to be -2. Or the chair says it's at 3, so it's 5 minus 3 would be -2. To get from 5 to 3, you need a -2. So if we subtract 2 from the hiker, we'll get the chair, okay? In the y direction, we have to subtract 4. And if you look at it, it makes sense because the chair is 2 to the right and 4 up from the hiker. So to accommodate for that, we have to subtract 2 and subtract 4 to put it from the hiker's perspective to the chair's perspective. Okay, any spot in the x direction will be 2 closer to the chair because the chair's been shifted to the right 2. Any coordinate in the vertical direction is going to be 4 less for the chair because the chair is 4 higher than the hiker. Okay, you're following me? Hopefully. I know this is a little deep, but I think that one actually makes it fairly clear, to be honest about it. This makes things a little bit more challenging in some ways. A man is standing watching a boat go by. At t equals 0, the stern of the boat is 10 meters directly in front of the man. The boat is traveling at 35 meters per second. And I drew in a coordinate system. I realized after I drew it in that the book is doing specifically z to be z to be vertical, like up and down, and x and y being the flat. And I did it this way because I was looking at it this way. So we're going to do it this way. I'm sorry about that. Okay. I think it still works. So they were going to be consistent throughout the problem. And this is a right-hand coordinate system. X to the right, Y up, and Z straight out of the screen. Okay, Z is straight out of the screen. So we're looking at this, and if we're doing, and you kind of have to visualize this man and this guy. Okay, the man is on the shore, and the boat is out in front of him. There's a guy on the boat. We're going to talk about the guy in a minute. But what are the transformations for t, x, y, and z going from a coordinate system with the origin of the man to a coordinate system with the origin on the stern of the boat? Okay, so one coordinate system is where that man is standing. The other one is on the boat. Well, time, of course, is the same for both of them, so we don't have to worry about time changing. In the x direction, okay, the x direction is to the right. The boat is moving to the right. The boat is moving to the right at 35 meters per second. So every second, it's 35 meters away. So that coordinate system is moving. So we have to know what time we're talking about something to convert this. At point 0, they're the same. Time 0, drop a 0 in there, they're the same. After 1 second, the boat has moved 35 to the right. So the man is going to say, oh, it's so far to the right, and the boat already is part way there. So it's going to subtract however distance it's traveled. Now for y, we're doing vertical here, and they're both the same. The shore and the water are the same, and this is why we're setting this up. Now in the z direction, the z is coming out at us. Okay, look at that. If you look at my thing, and remember we did electricity, right-hand rule, x, y, z is coming out of the screen, so it's a dot there, not the little cross. It's a very large dot, but that's the dot. So that means that to go from the man to the boat, you have to add 10, because the boat is 10 meters in the negative direction. And so it's further away from anything in the z direction, and we have to add 10 to catch up to where the man's perspective is. Okay? All right. I hope this is making sense. I know this is kind of confusing, but we try. Okay, so if the guy in the boat is walking at 2.5 meters per second, what is the speed of the guy from the perspective of the man? So the man on shore is watching, and the guy is walking on the boat, and the boat is moving. That means that he's going to add those two speeds together. And so from the perspective of the man, the guy is walking at 30, or is moving at 37.5 meters per second. 35 because he's on the boat, and the boat is, and 2.5 more because he's going 2.5 more because he's traveling with the boat, and so that adds to the speed. Now, what about the speed of the man from the perspective of the guy? If you're the guy looking at the man, what is his speed? Well, it's the same, but it's the other direction. If you're on the boat is moving and you are moving, and the guy on shore is apparently moving backwards. Now, this is relative, and the reason this makes a difference, or this is important to us, is an example of this, an application of this, what I'm trying to say. Sorry about that. My brain's having issues this morning. If you're sitting at a train and you're watching the train go by, sometimes if you kind of refocus, you feel like you're moving. Well, that's relative. Relative to the train, you are moving. If you were a person on the train, you would watch a car fly past you backwards, back towards the back of the train. That's the idea here, okay? All right. Now, if the boat, after 2 seconds, sees a bird at this position, what is the position of the bird from the perspective of the man? And I realized I set up my XYZ coordinate systems to do this with you, and then I realized that I had done it differently when I wrote it, because right now we have a bird swimming underwater, 3 meters underwater, which is kind of cool, actually, but not what I intended. Okay, so if the bird from the position of the boat is at 4, -335, where is it according to the man? Well, we have an equation here for x of b equals xm minus 35t. We got that on an earlier slide. We're simply going to can do algebra to convert this back, okay? And so now the x of m equals xb plus 35t. So xm is 4 plus 70, which is 74, which if you stop and think about it, after 2 seconds, the boat is 70 meters to the right, probably way off screen. It sees a bird 4 meters in front of it. From the man, that's 74 meters to the right, because he's got to catch up to the boat 70 meters, then 4 more meters to get to the bird. The y's are the same, so that's just -3, so the bird is 3 meters underwater for both of them. And then z is this in and out of the screen direction, and we have to rearrange the original equation we came up with, and that gives us 25. 35 minus 10 is 25, because if to the boat, the bird is 35 meters towards the front of the screen, out of the screen, but the man is already 10 meters that direction, so it's only 25 meters for him. Okay, this is the easy part of the chapter, okay? Galilean transformations are classical. This has been around since the 1400s. I think it's 1400s. This is the old stuff. We're going to get into the fun stuff in the next section. So, text me. Text me where the guy is. Text me where the guy is. All right, thank you. We'll talk again tomorrow about some more of this chapter.